All right, we are on chapter 13. We are looking at the kinetics, the change of the rate of a reaction, chemical reaction. We're going to be looking at what we can do to change that rate, what factors are involved there. Before we do that, a couple more things we need to talk about, but I have a question for you first. All right, we just learned about exothermic, endothermic reactions in the previous lecture. So of these three reactions, okay, exothermic, endothermic, and energy neutral, which do you think has the fastest rate? Which do you think is fastest? Now at this point, some of you might realize, hey, she kind of adds tricky questions. You'll remember about that heating curve one, and you're like, I'm not going to fool for it this time. Most people would say, well, exothermic releases energy, okay? That must be the one that might be fastest, but guess what? It's going to be one of those trick questions where, again, it will depend on the reaction. And there's something else we're missing besides just where the reaction starts, where the reaction finishes, to what is actually going on to make the rate faster or slower. You ready for it? Here we go. We need to also identify, there we go, the activation energy. All right, let's look carefully at this. The activation energy is the energy that must be overcome for a reaction to move forward. All right, this is the minimum amount of energy reactants need in order that they become products. Now, if you look at this picture here, okay, you see that we have the same thing as before. We have the reaction coordinate on the bottom. We have energy on the Y here. We have higher energy, lower energy. We have the reactant starting somewhere. We have the products finishing somewhere. Okay, so just by looking at that, we can say, hey, this is an exothermic reaction, okay, because energy's been released. But now there's something else that's been added, and that's kind of what's going on from how we get the reactants to turn into products. All right, so we said that all bonds, when they're broken, takes energy. Okay, so there's some minimum amount of energy needed. Okay, this is this hill that we have to get over in energy. Some amount of energy has to be put in, okay, in order for this reaction to start taking place. And when we get to the top of this hill, we call this the transition state. So this is the peak where now you have reactant bonds just starting to break and the product bonds just starting to form. All right, so the height or the amount of energy here, the magnitude of this activation energy, so this energy, if you kind of bring a dotted line out from reactants, it's the change in energy here between where the reactants start and the top of this peak. Now, the magnitude of this gives you a clue on the speed or the rate of this reaction. If you have a large activation energy, that means you need to get to a pretty high amount of energy before you can go from reactants to products. This will be a slower reaction. Where a small activation energy, the reactants don't need that much energy in order to get going over this little hump, that will be a faster reaction. It does not matter if it's going to be an exothermic or endothermic reaction overall. That's the overall change in energy. This is dealing with this little bit of energy that you must be putting in before those reactants can get over. So minimum amount of energy to overcome for the reaction to move forward. Okay, so you have to have these reactants. They have to collide, but they have to collide with enough energy in order to get over this peak. If there's a collision, but they don't have enough energy, even though they collide, even if they have the right orientation, no product will form until they get this activation energy. All right, I think that covers all of that. Let's look. Oops, my screen says waiting. Maybe yours showed up there. All right, let's look at these two reaction coordinates. We have A and B. All right, and now that we've talked about this should be pretty easy. Which one do you expect to go faster? Okay, you have A or B. And we would all say A, right? You can see we're comparing the activation energy here. All right, this is the activation energy for A. And if you look here to here, the activation energy for reaction B, it's much greater than for A. So A will be faster. All right, now here's another question. What is faster? And let's just look specifically at A only. Okay, so looking at A, Is the forward reaction or the reverse reaction faster? All right, so look at the activation energy that you would have for the forward, okay? That would be this activation energy. So this is the activation energy for the forward. Let's compare that. What would the activation energy for the reverse be? That would be going from products to reactants, going from here to reactants, so going the opposite way. So if you bring this out here, this value right there would be the activation energy for the reverse reaction. So in A, if we're comparing the forward reaction to the reverse reaction, the activation energy for the reverse is much smaller, so that would be faster than the forward reaction. All right, so use activation energies. Big one, the reaction's going to be slower. The reactants have to get a lot more energy, okay, before they can get over that hump. Let's look at this, and let's actually try to do some. All right, so we're going to use this data. So there's a bunch of data right here, and I want to make sure you guys yourself can sketch this out and answer these questions on your own. We'll work through the first one a little bit together. So here is the different reactions. We'll look at reaction 1 first together. That's right here. I'm giving you the energy of the reactants, the energy of the products, and the energy of the transition state. So first off, sketch it. Then decide if it's endo or exo, and find the change of energy for the reaction and find the activation energy. All right, so for this first one, it looks like the reactants start at 50. And it looks like our products are finishing at 60. Okay, it's a little hard to kind of draw. I should have made these bigger. And our transition state is at 70 kilojoules per mole. We're going to kind of go right to there. So what does this look like? We're going to go like that. Okay, we have that energy value there. So this was 50 kilojoules. This is at 60 kilojoules per mole. And this right here is 70 kilojoules per mole. All right, so just by looking at this reaction, is it exothermic or endothermic? And here you want to find, okay, reactants or products minus reactants, and that will be our change in energy for the reaction. You can see that the products finish higher than the reactants, so this should be endothermic. And we can find the change in energy. And this would be our products minus our reactants. And so this is positive 10 kilojoules per mole. And then we can find our activation energy. Now this is the difference between where the reactants start and that top of the peak of the transition state. So this amount right here is called our activation energy. Oops. Activation energy for this one between 70 and 50 should be 20 kilojoules per mole. All right, so that was for that first one. I'm going to pause this for you guys for a second, and then I'll fill out what I have for reaction 2 and 3 and see if you can do those on your own as well. All right, I have filled it out. I hope you have gotten yours filled out as well. We did one together. Looking at the second one, you can see where the reactants start is at 20 kilojoules per mole. The products finish at 10 kilojoules per mole, and the energy of the transition state was all the way up at 90 kilojoules per mole. So this is an exothermic reaction. I calculated the activation energy to be 70 kilojoules per mole, and the total change of energy for the reaction would be negative 10 kilojoules per mole. All right, the other one here, this time we're kind of switching those values of reactants and products. We're starting the reactants at 10 kilojoules per mole. The products finish at 20. Okay, it's higher up, so you can see this is going to be an endothermic reaction. We can find that change in energy to be a positive 10 in this case. And then the transition state was up at 90 as well. So our activation energy then would be the difference from where the reactant started at 10 all the way up to 90, so 80 kilojoules per mole. This is something that you should be able to do and then you can use this to talk about the rate of the reaction as far as the activation energy goes. And then in the next couple lectures, we're going to look at, well, what can we do to change the rate? Okay, and so we're going to look at, well, can we get a different reaction so that we have a lower activation energy? Can we do something to the reactants to get them to go over that hump faster? Can we have more of them around? Can we increase temperature? So we're going to be looking at some of those factors involved in order to speed up a reaction. So there we go for the end of this lecture. See you next time.